Hello everyone, this is Jim Corkins, and we are moving on to forces. So this is really the second major chapter in Physics 121 and 111 and also 101. So please begin the reading if you haven't done so. Coletta chapter 4 and 5, OpenStax chapter 4 and 5 if you're in Physics 111, and OpenStax chapters 5 and 6 if you're in Physics 121. Okay, so before we begin talking about forces, we're going to have to talk about some terms. And those terms are basically what's mass, what is volume, what is weight, and what is acceleration. Okay, so we're going to have a pretty solid understanding of those concepts before we actually talk about what is force and also Newton's three laws. So mass is basically just how much matter an object has, okay? And I'm going to mark up this document, and how you do that again is you go to the comments area, hit comments, and then you'll notice it pops this bar out to track the comments. Then you want to minimize that bar again. And now I could use the little pencil, right? I could use the eraser pencil, shapes, things like that, and I could also change the color of the pencil up here. So mass is just how much matter is that an object has, and we are going to be using SI units. So this would be measured in kilograms. Okay. So for example, if you've ever been to the gym or anything like that, you've probably seen a barbell plate that says 45 pounds, but also 22 or 22.5 kilograms. Well, 1 kilogram, which is the amount of matter, is actually equal to, or analogous to, I should be careful here, but 1 kilogram is 2.2 pounds, okay? But a kilogram is not a pound, is not relatable to pound, okay? When we're talking about weight, okay, so when we talk about pounds, we have to talk about weight. So back to here, the European unit of mass is kilograms. Okay, but in America, that is slugs. Okay, so the American unit for matter, which is in kilograms, is European is kilograms, is slugs, and that is 0.0685, and it's slugs, just like the little critter slugs. Okay, so these are measurements of matter. Okay, like your fingernails, your hair, that kind of stuff, right? So if you want to lose mass, well, you'll have to get a haircut, or you'll have to cut your nails, or something like that. There's a lot of ways to lose weight without actually losing mass, and we'll talk about that. So volume is just basically how much space an object occupies, and that unit of measurement is typically in meters cubed, okay, or cubic meters. All right. So I know they're, like, for example, in kilograms you have grams, you have centigrams, but typically everything is measured in reference to kilograms. With volume, it's a measurement of space, which actually is a measurement of distance. And this is a three-dimensional distance. So if you think about a cube, right? A three-dimensional cube, right? It's got a length, it's got a width, and it's got a height. So that is length times width times height, and those are all in measurements of meters. So that's what they're talking about when they're talking about volume. It's this three-dimensional size of an object. All right. Weight is a little bit different. Weight, you have to actually consider an object's mass, right? But it's mass times whatever acceleration due to the planet that they're on. So, as we have learned, the acceleration due to the Earth that gives objects close to the surface on average is 9.8 meters per second squared. Excuse me. So an object's weight is its mass in kilograms. It's a kilogram times the acceleration is meters per second squared. Okay, and that is also called a Newton. Okay, so here we go. Let's just draw an arrow there. So mass times gravity is 1 kilogram meters per second squared. So 1 kilogram meters per second squared is 1 Newton. Okay, so that is essentially the measurement of weight. Now, if you went to a different planet, so on the Earth, gravity, the acceleration of gravity is 9.8 meters per second squared. So if I weigh roughly like 100 kilograms. So my mass is 100 kilograms. So that means between the both of these, my mass times gravity is going to be equal to 980. So my weight is going to be, what is that? 980 newtons. Okay. But again, if you've ever been to the gym, you've seen this relationship, 22.5 kilograms, and they'll also have written on it 45 pounds, right? Well, they're relating mass, and pounds is a measurement of weight, which is mass times gravity. So it's kind of weird. I don't like the way they do that, right? If they're going to do that relationship, they should do mass times gravity here, which would be 22.5 kilograms times 9.8 times 9.8. That's 220.5 newtons. So, what was that? Darn it. 22.5 times 9.8. It's roughly 10, so 22.5. 220.5 newtons. They should be doing this, right, to relate it properly to pounds. I'm not sure why that is the case, but roughly 220.5 newtons is 45 pounds. So pounds is a measurement of weight, okay? And if we are going to make that relationship, roughly 1 kilogram is equal to 2.2 pounds, or lbs is another measurement of pounds, another way to write pounds. So it can get a little confusing when they're talking about weight, because we've all seen this relationship of kilograms to pounds, but really it should be newtons to pounds. So, but in this class, we're just going to keep everything in newtons, okay? So, again, the SI units, not the imperial units. Imperial units is pounds. Acceleration, again, we've studied that is your change in velocity, and that is measured in meters per second squared. Okay? So that's the basic terms that we're going to be talking about, is mass, volume, weight, and acceleration. Okay? So there is a relationship, though, again, to go a little bit deeper into mass and weight. Again, we're going to be dealing with mass as a unit in kilograms and weight as a unit of newtons. Okay, there might be some homework problems when they're referring to weight in pounds, but again, weight is equal to mass times gravity. Well, mass is just mass, which is the amount of matter of an object is, right? The one thing about weight, which we have to be careful of, again, is if your weight here on the Earth is if you had a 1 kilogram object and that object was on the Earth, that would be 9.8 meters per second squared. So that object would have a weight of 9.8 newtons, right? Well, if you're on the moon, if that 1 kilogram object was on the moon, the acceleration of the moon is 1.625 meters per second squared. So that object would only weigh 1.625 newtons, right? So if I weigh, let me go back a little bit. I weigh 980 newtons, okay, which is 100 kilograms. So I'm 220 pounds, give or take. Probably more give than take. But anyways, my point is, I wish I weighed 100 kilograms. I'll just be honest. I weigh a little bit more than that. But my point is, I'm going to get there. I'm on a diet. I'm going to get there. But I should weigh 980 newtons on the Earth. But if I went to the moon, my 980 newtons would actually only be 163 newtons. So that's the best weight loss program I could think of, is if I just moved to the moon, right? And then I could just do all the pull-ups I want. It'd be really, really easy for me to do that kind of pull-ups. So, joking around, joking aside, but this is a good relationship. This is a good thing to put together, that your mass and your weight are two different things. If I were out in space away from any planets, or if I was in free fall, just falling to the Earth, I would basically weigh nothing. Okay? So I would weigh nothing at all. So now we've made it to Newton's 3 laws, all right? And in this time, Newton's laws were actually revolutionary. They changed the way that we looked at the universe, really. And he was a significant scientist that really changed really the entire world. So, and it really, he's well known for these laws. These are his major contributions. He has a lot of other contributions, but these are the 3 main ones that really changed a lot of things. So to just sum it up, we're going to just go talk about it, and then we're going to talk about these 3 laws here just all together, and then we're going to talk about them one at a time, and little idiosyncrasies about each one. Okay, so they seem pretty clear cut, but they're actually very weird. And counterintuitive, really, when you think about it. I maintain that the reasons why we have a hard time with these laws is not that they're logical. They're actually really illogical when you think about it for a little bit. So the first law is this. So let's get to it. The first law, which we're going to go through in a little bit, is that every object will remain at rest. An object at rest will continue to stay at rest. Okay, it wants to stay at rest. Or if it begins moving, it will want to continue moving at a constant velocity in a straight line until acted upon by an outside force, right? So that's also called the law of inertia. Okay, so that's also called the Newton's first law of inertia. Okay. The second law makes a quantitative relationship between mass, acceleration, and force, right? So just to sum it up, basically a force is equal to mass times acceleration. Another way of looking at it is this: if you have a constant force acting on an object, so that's a constant force acting on an object, and you want to compare the mass to its acceleration. If mass goes up, and that's a denominator, and you're comparing it to a numerator, the numerator is going to go down proportionally, right? Or you could say this: if you have a constant force acting on an object, you have a mass. If the mass goes down, then the acceleration should go up if the force is a constant, right? Otherwise, if you have a mass and acceleration working on an object and those both increase, the amount of gravitational force, if an object's mass is increasing and the acceleration is acting on it, then the amount of force that's going to act on it is going to also increase, because it's numerators comparing to each other. Okay. Finally, Newton's third law. If you have an object, objects are always equal and opposite, essentially. So this is basically force pairing. Oh, and Newton's second law is just F equals ma. So force pairing, forces are always equal and opposite. If I pull on you, you will pull back on me an equal and opposite amount. Okay? And that's actually probably the hardest one to understand. Okay? All right, well, let's go ahead and jump into it, and let's deal with the law of inertia. Okay? So Newton's first law of motion, the law of inertia, essentially, it originated with Galileo. And he did not rip it off. He just kind of applied more to it, right? So, again, every object will continue to stay at rest, or if they are moving, they will continue to move in a constant velocity unless they are acted upon by an outside force, okay? So, Galileo, brilliant man too. Kind of a tragic story, but he had basically hypothesized that the sun is the center of our solar system, and the church at that time maintained that the Earth was the center of the universe. And so they basically put him in prison and made him recant that. Or I think face death, something like that. So he ended up recanting that, but it was correct. We all know it now, so that it's kind of a terrible story. But the cool thing is that he was able to make a lot of brilliant discoveries before that, right? Before he got basically pushed out of the church. And so the first one is this, and we've all heard the story of the Leaning Tower of Pisa, not pizza. I love pizza. It's not the Leaning Tower of Pisa. It's the Leaning Tower of Pisa. Galileo basically suggested that an object, if there was a lack of air friction, a state of free fall, and we studied this before, that if you took out air resistance, two objects will hit the ground at the same time. And I showed a video of Falcon Feather and a hammer on the moon. On the moon, there's no air. Two objects are going to fall at the same rate. Okay, so he was exactly correct on that. Another concept that he suggested was this. He had a metal ball in a bowl, and he let it go, and the metal ball would roll down and roll across and get about to the same final position that it started at, the same height, right? So if it started at a height over here, a height this high over here, it ended at about that same height. You know, again, friction is at play, so it wouldn't roll like this forever. It would then come back across and roll. But if you didn't have friction, it would come back to the height and roll back and forth forever, right? Well, he then was saying, well, is it the fact that this angle is the same as this angle right here, meaning this angle here is the same as this angle? So what he did is he had a bowl made that was really weird shaped. It was steeper on one end than on the other, right? So these two angles are equal here, but this angle right here is much bigger than this angle right here. So it's a little small. And what he found out, that when he rolled it, it came back up to the same height regardless of the angle. Okay. Well, then he said, well, does the angle even matter? What would happen if I just didn't have this over here? What would happen? And what he hypothesized was that if you let it roll, it will continue to roll forever if friction was not at play. And so this object would continue to roll until it came up to a position where something brought it to a stop, like the side of the bowl that would bring it to a stop. Otherwise, it would just roll forever across this floor. The only thing that was bringing it to a stop and reversing it was this final position here. So this is the first basically introduction of the idea of inertia being at play, where an object that has a mass will continue moving forever at a constant velocity unless something acts on it, like the side of this bowl, which will then change its direction but also then slow it down too. So he never said that in that way. He just kind of made this observation. It was Newton that then put it together in the Newton's first law. Okay? So this concept completely changed how we were operating before, and that was because Aristotle had basically the opposite assertion, right? And so this observation that Galileo made, which then was later then reduced into its basic components by Newton, was a very significant contribution and changed the way that we approached everything as far as the ideas of velocity and motion. So the concepts of this is kind of interesting, right? So if you've been sitting at a stop, you have a hot cup of coffee, you're sitting at a stoplight, and then it turns green. Do you then start to hit the accelerator pad and then drink your coffee at that moment? Or do you wait until you hit a stable velocity, or a stable speed, I should say, and at that point, do you choose to drink your coffee? Which one would you do? Or if you're slamming on your brakes, is that a good time to drink your hot coffee? So that's the kind of concept of inertia, right? So if you're on an airplane and they say it's free to move about the cabin, you're just kind of walking around the airplane. You don't even notice if you feel the plane rumbling, but you wouldn't even know if you're moving or not if there weren't clouds in the sky, right? So it's the fact that the acceleration, that if you're in a state of acceleration, meaning speeding up or slowing down, that you actually do feel your inertia working on you. And that's because you have an outside force working on you. You want to stay moving in that plane. And then if the plane starts to slow down, well, then you will absolutely feel your inertia working on you. You're basically your own mass. And when I say inertia, really I'm referring to your mass in kilograms, right? So the concept of inertia is in reference to mass. Okay. And so this concept is actually this concept of inertia is resistance to change in motion. It's your mass resisting the change in motion. Okay. You're staying at rest. If you're at rest, your mass wants to stay at rest, right? In order to move, something has to push you, right? An actual force has to be applied to you, right? Which will then cause an acceleration and so on. So let's do some problems and see if you can properly apply that concept of inertia to these different situations. So go ahead and let's do this problem. If you have a tablecloth that is quickly pulled from under a dinner table plate, the dinner table plate will stay in place, right? So you have a nice slick cloth. You have a dinner table plate that's smooth on the bottom, so there's no friction or anything working on it. And you walk up and yank it, you'll notice it stays in place. Well, why does it do that? Number one, there's an opposing horizontal force acting on the dinner plate all the time. There is an action-reaction pair of forces. Gravity is opposing the tablecloth's inertia, or the dinner plate has inertia. What do you think? Well, if you think about it, this dinner table plate, again, is wanting to stay at rest. It's at rest, and it wants to stay at rest. So 4 is the answer. And so the dinner table plate has inertia, and that inertia is tied to a velocity of 0. So it's going to stay at rest unless a force interacts with it, right? But the only force that would interact with this is friction in this case. And since I said there was no friction acting on it, you could bet that if no forces are interacting with an object, well, that object's just going to stay at rest. Okay? Let's try another one. The force required to maintain an object at constant velocity in outer space. So we've all seen space movies. So suppose there's a spaceship flying at a constant velocity. So it's got a velocity vector, but it has no acceleration vector. Okay? And it's moving to the right. Okay? What force is needed to maintain it at that constant velocity? 0, the mass of the object, the weight of the object, or the force required to stop it. So go ahead and answer the question and really think about your own ideas and belief systems and what is your reasoning for choosing the object, 1, 2, 3, or 4. Okay, so pause the video and try this out. Well, again, if an object is moving at a constant velocity, it doesn't need any force to let it continue moving at a constant velocity, right? If there's, in the absence of any forces, there's no friction in outer space, there's no gravity, like if you're away from any planets, there's no gravity or anything like that. So there's no possible forces that's going to be applied to this. So if it's already moving at a constant velocity, it doesn't need an actual force to keep it driving, right? So it already has inertia, and it's going to be moving in a straight line forever. So the force required to maintain that constant velocity in outer space is 0. Okay? Another situation. We've all been in elevators. If you've ever been in a big building in Central Phoenix and gotten in the elevator, you'll notice when you get in an elevator, you first press the button to go up. How do you feel when you first press the button to go up? So if you happen to be standing on a weight scale at that time, and you're at rest in the elevator, press the button, and the elevator begins to accelerate upwards. So how do you feel when that is happening? Do you feel heavier? Do you feel lighter? Or do you feel the same weight as you're speeding up, as you're moving upwards? What do you think? So pause the video. Again, I want you to think about what your own belief system is, but also I want you to apply Newton's first law. And sometimes those two will directly conflict with each other, right? So I want you to apply Newton's first law, and also I want you to think about what your tendency is, and see if you could resolve that, okay? So pause the video and answer the question. All right, well, so you're standing on a weight scale and you begin to accelerate upwards. Well, you want to stay not moving, right? So you want your velocity to be 0. However, the bottom of the elevator is going to begin moving upwards, and not only that, it's going to begin accelerating upwards. So you want to stay at rest, but the elevator is going to be applying a force to you, okay? So it's going to be applying an upward force to you to get you to move upwards, to get you to speed up as you're moving upwards, right? So the fact that you want to stay still means you're resisting that force working on you, which means that you are going to start to feel heavier, right? So if you've ever been in the bottom of an elevator, you hit the button, it starts to speed up as it's moving upwards. That means the bottom of the elevator is forcing you upwards. You're going to feel heavier than you normally do, okay? But what you may have noticed is once you hit that constant velocity, okay, maybe you're going upwards now. You're still maintaining going upwards. Let me do something here. So let's say that you're on that elevator and you're moving upwards. So you were accelerating upwards and you were feeling heavier as you were accelerating upwards because the bottom of the elevator was forcing you up. And I'm going to change this to up. Okay. But now you've hit this constant velocity, right? And so if you've ever felt that way in an elevator, you hit that constant velocity. Well, now, how do you feel now? Do you continue feeling heavier? Or do you start to feel lighter than you normally do? Or does it stay, or do you feel your regular weight? So how is your weight scale recording compared to your actual weight? All right. Well, again, I want you to think about when you want to drink coffee. Do you want to drink coffee when you're speeding up, when you're slowing down, or where you're driving at a constant speed? Okay. And so this is related to that constant speed part, right? Well, what you should feel is that you should feel the same weight as you normally do if you're moving at a constant velocity, right? That's, again, when you're on a plane and the plane's flying at a constant speed and the pilot says you could roam about the cabin. And so at that point, you could actually get up and you feel like you're not moving. It's really cool. And same thing when you're driving at a constant velocity in your car. You could drink your hot coffee because you feel like you're not moving at that point. Okay. But now you're moving upwards and you start slowing to a stop, right? Actually, let's do this. Moving up, actually, let's not change this one on this. Let's say you're at the top of an elevator and you're at rest, and now the elevator begins to move down, right? It begins to accelerate down. And that means the bottom of the elevator is dropping out from underneath you, okay? And you are moving down and speeding up as you're moving down. Now, that's kind of like jumping off a diving board, right? How do you feel when you jump off a diving board other than you might die? I'm so scared of heights sometimes. But if you've ever been on in the elevator at the top of the shaft and it starts to actually, really in older elevators, it used to drop really rapidly. And I used to feel a little scared when it would happen because I would actually feel lighter than I regularly would, right? You will in whatever case, but in an elevator that really starts to drop really fast, in fact, if it starts to drop close to gravity, if it's actually accelerating down closer to gravity, well, then you're in free fall, and you're just kind of falling, okay? Old elevators didn't drop close to gravity, but it got pretty close. It was kind of scary sometimes. So if you are in an elevator and you are at the top of the elevator shaft and you're at rest, and then it begins to move down, for a moment you're going to be accelerating down, and that is going to make you feel lighter than you regularly do. Okay? Well, I hope that kind of helped you understand Newton's first law, the law of inertia. Okay? Let's move on to the second law. And the second law is actually kind of easy to understand, really, because it's just a quantitative relationship between acceleration, force, and mass. Okay? So again, you have force over mass is equal to acceleration, or another way it's kind of written is force is equal to mass times acceleration, right? So to answer these next set of questions related to this, okay, you're going to be doing some type of comparison of acceleration, mass, and force, okay? So you'll see me write probably this very equation right here a lot and do some comparisons that way, okay? So let's try it. Just to let you know, this is before we actually do those problems. I apologize. This is a comparison of force is equal to mass times acceleration, right? So if you have a force of pushing a brick right here, and it pushes it with a little bit of force right here. Well, now that what they're saying is this, is if that force is increased, that's then going to increase the acceleration. The mass is going to be a constant because this brick is not changing its matter. It's got the same stuff here as this other brick here, right? So what they're doing is relating force to acceleration, right? Since mass is a constant, force, if force goes up, the acceleration is going to go up, as long as mass is a constant, okay? What they're saying here is this. If we're going to probably make, we're going to do this relationship. If your force doubles here, so your force doubles here, then that means, again, that your acceleration is going to double. And I should do this. Your force doubles, then your acceleration is going to double. But over here, what they're saying is this. If you have one force that goes up, and I'm going to do acceleration is equal to force over mass. If your mass goes up, but your force is a constant, that means your acceleration is going to go down, because mass is inversely proportional to acceleration. And so what they're saying over here is the same thing, right? If your mass has gone up by 2, the acceleration is going to go down by 2. Over here, what they're saying, again, if you push with the same force, just one hand, that's going to be a constant. Here they're saying if the mass triples down, then your acceleration is going to triple. Actually, if your mass triples up, I should say, if you have 3 bricks, then your acceleration is going to triple in the upwards direction, in the downwards direction, I should say. Over here, they're saying they're varying 2 things at the same time, right? So we're going to do acceleration is equal to force over mass. You've doubled the force, but also you've doubled the mass. And so the acceleration is going to cancel out. If this is going up, and that means it's going to lower the acceleration, right? So if your mass is going up, if your mass is going to go up, let me draw that. If your mass goes up, your acceleration is going to go down by 2. If your mass goes up by 2, your acceleration is going to go down by 2. But then, if your force goes up by 2, your acceleration is going to go up by 2. So they basically cancel out. If your mass goes up, your acceleration is going to go down. But if your force goes up, and since it's a numerator, your acceleration is going to go up. So your acceleration is going to be the same. All right? So this is one slide trying to show you that relationship of force, mass, and acceleration. Okay? But let's try it with actual problems. We're going to do the same kind of thing, but we're going to try it across a bunch of problems. Okay? So in a race, you have 2 carts. One cart, so this cart right here is, we're going to call this cart, the cart itself is 1 kilogram. And this cart is 2 kilograms, right? And they're going to have the same force applied to it. So let's say this fan applies 2 newtons of force here, and this is the same fan, so it's applying 2 newtons of force here. Okay, so actually let's make it 4 newtons. we'll put 4 newtons of force. So both fans are the same type of fan, and they have the same setting, so they're both set to high, which is 4 newtons of force. So the cart is going to be pushed to the right with 4 newtons of force, and this cart here on the bottom is 2 kilograms. This cart on the top is 1 kilogram. What I want you to do is sketch the position versus time graphs for both carts at the same time, the velocity versus time graphs, and the acceleration versus time graphs for both carts. Okay? So go ahead and try that out. All right, well, let's do the acceleration versus time graphs. I actually changed the top graph to red and the bottom graph to blue, so when we draw on here, we're drawing 2 lines with different colors. That way it's easier to distinguish between the 2 carts. So the red cart is a 1 kilogram cart, the blue cart is 2 kilogram cart. So if you'll notice, basically this is just that force is equal to mass times acceleration here. So this red cart is going to have an acceleration of 4 newtons over 1 kilogram, which is going to be 4 meters per second squared. Okay, and again, I got that from basically acceleration is equal to force over mass. Okay. The blue cart is going to be accelerating at 4 newtons over 2 kilograms. So that is going to be 2 meters per second squared. Okay? All right? So over here, what that means basically, if this is and they're both accelerations are going to be to the right, so it's going to have a positive acceleration. The blue cart is going to have an acceleration at 2 meters per second squared. And I should say a positive 2. And the red cart is going to be double that acceleration, right? Positive 4 meters per second squared. And so what that means is the velocity versus time graph is going to have a slope of a positive 4 meters per second squared, and the blue cart is going to have half that slope. It's going to be positive 2 meters per second squared as its acceleration. Okay? And what that means is it's going to take a longer change in time. Its change in its position is going to be a lot less drawn out. And the red cart is going to be a lot more slopier, or steeper, I should say. Right. So it should look something like this, right? You're going to have straight lines. It's going to be a constant acceleration as long as the force is constant, right? And so since the force is in both cases, 4 newtons, this one is going to be 4 meters per second squared. The heavier object is going to be 2 meters per second squared. It's got more inertia. It's got twice the inertia of the red object, the red cart. And so their velocity versus time graphs are going to be very different too. They're going to have 2 different slopes for those. And that translates to you having a lot steeper change in position over time for the red cart, the 1 kilogram cart, and the 2 kilogram cart. Okay? Well, now that we've practiced it a little bit, let's see if you could apply it to different situations. Right? Suppose you're riding in a cart full of bricks, okay, and your friend is pushing you with a constant force of 100 pounds. So they've attached like a weight scale to the back of the cart, and your friend is just maintaining that weight scale at 100 pounds of force as he pushes on the weight scale, and the weight scale then pushes on the cart. And so you're sitting in there with a bunch of bricks. Well, now you begin to drop bricks off the cart one by one. So as you do this, what should happen to your acceleration? Should your acceleration increase? Should you decrease, or should it stay the same? So what do you think? Go ahead and pause the video and apply Newton's second law to this case. Well, again, Newton's second law, acceleration is equal to force over mass, right? And so the force is being maintained at 100, the force is being maintained at a constant 100 newtons of force, right? So that's a constant. And so now you are dropping the mass of the total object, right? You're dropping bricks off there. Well, as long as your friend continues to push at 100 newtons, that means your acceleration is going to go up. And if your acceleration is going to go up, that means your speed is going to increase over time. And so what that means is overall your speed and your acceleration is going to increase. Okay? Pretty cool. How about this? Suppose your rocket engines are firing in space, and space is a vacuum, by the way. Will the rocket's velocity be constant? Will it increase for a while and then be constant, or will it increase forever? So what do you think? What's going to happen when you're in the vacuum of space? Will you continue moving? Will you move at a constant velocity, which is 1? Will you increase? Will you speed up for a while and then hit a constant velocity? Or will you increase forever, right? And we're talking about the Newtonian universe, not the Einstein universe, okay? So what do you think? Well, if your rocket engines are firing, that means you have a force being applied to you the entire time, right? And since your mass isn't changing, well, what that means is, here we go, you have a constant force being applied to you, right? And your mass is also a constant. Well, actually, you have a force being applied to you, right? And that would be a constant force being applied to you. And your mass is also constant. Well, what that means is you are going to have a constant acceleration, which means this: you will have a velocity vector and you will have an acceleration vector. And since those two are constants, your acceleration vector is also going to be a constant. And so this is this, which means this: you should speed up forever. So your velocity should be increasing forever. Now, if you were considering the fact that speed of light if you're considering speed of light, yes, it would increase for a while, then stay constant. But most of us would think that just like if I'm hitting the accelerator pedal in my car, well, if I hit the accelerator pedal for a little bit, I'll increase in speed for a little bit, and then I'll hit a constant speed. And that's because air friction is working on me, right? But space has no air friction. It's a vacuum. So essentially what the thing is you in the Newtonian universe, it should increase forever. Okay? All right. Let's do a last one. Consider a cart pushed along a track with a certain force. If the force remains the same while the mass of the cart decreases to half, what should happen to the acceleration of the cart? So this is a cart being pushed along a track with a constant force. And the force is going to maintain, the force and the force is going to be constant. Now the mass of the cart is going to drop. What should happen to the acceleration? Well, again, force is equal to, well, acceleration is equal to force over mass. So force is a constant. Your mass is going to drop. That means your acceleration is going to go up. So that means if your mass drops by 2, your acceleration is going to go up by 2. So that means your acceleration is going to double. Okay? I guess we could continue moving, I suppose. If a cart is pushed with to the right with a constant steady force, what should the acceleration versus time graph look like? So you have a cart being pushed to the right with a constant force. What should the acceleration versus time graph look like? Should it be A, B, or C? Well, whenever I get something like this, I like to apply numbers to it, right? So let's say this object has a mass of 3 kilograms, right? And let's say a force is being applied to it of, I don't know, 12 newtons. Okay? Well, starting with Newton's second law, force equal to mass times acceleration. Acceleration is equal to force over mass. So that is going to be 12 newtons divided by 3 kilograms, which will be, and since those are both constants, I should get a constant value of 4 meters per second squared, right? And since I'm not changing 12 newtons and force is not changing, mass is not changing, so the acceleration should not change as well, right? This is showing you have a 0 acceleration here per second squared, and then it goes up to something like 8 meters per second squared, right? And this is saying it starts out at 8 meters per second squared, your acceleration, and then your acceleration drops to 0 meters per second squared. This is basically just showing a positive 4 meters per second squared the entire time. And that is what we're looking for. So the answer should be C. And there you go. Here's a velocity versus time graph. Which of these force versus time graphs match this velocity versus time graph? So what do you think? Okay. So start off simply and just translate this velocity versus time graph to constant velocity, speeding up, slowing down, and then to speeding up and slowing down, and then also the acceleration of 0, acceleration of positive or negative, right? So use those terms to translate the velocity versus time graph, and then use that to then maybe turn it into an acceleration versus time graph. So an acceleration versus time graph. And then that acceleration versus time graph should reflect the force versus time graph. Okay? So try it out. Again, basically the mass is constant of this object. All right. Hit pause and try it. Well, here we go. At this point right here, you have this line is a horizontal line in a velocity versus time graph. And we know that means that this object has no acceleration during that point, right? So this is a constant velocity, which means the acceleration is 0, okay, at that point. And then it's going to go to a stage here, right here, where it starts off at like maybe 1 meter per second, and then it goes to, so if this is a velocity of 1 meter per second, and then it goes to a velocity of 3 meters per second, right? So if it's going at positive 1 meter per second initially, and then in the end it's going at 3 meters per second, what would you call that? Speed up, slow down, constant velocity. Well, I would call that speeding up, right? And so this slope here is going to be the acceleration, and since that slope is positive, that's going to give us a positive part of our graph. But that slope is constant, so it's going to be a straight line above the 0 mark, right? And so that's that part. And then it goes back to a stage where it's now at a constant velocity of 3 meters per second, which means it has no acceleration during that part, right? Well, that acceleration versus time graph would only be different, okay, since force is equal to mass times acceleration. Mass isn't changing. The force graph is just going to be a mass times that acceleration, right? So all you're going to be doing is applying 0 times, if this object was 2 kilograms, for example, it'd be 0 times 2 kilograms, which is just 0, right? So you should have a 0 part here, and then a 0 part in the end. This acceleration here, if it was, let's say that acceleration is 2 meters per second, 2 meters per second squared, right? Let's say this acceleration took place over the period of 1 second to 2 seconds, right? So it went from 1 meter per second to 3 meters per second. So 3 meters per second minus 1 meters per second divided by 1 second. That's the delta t there. That would then be, the force would then be 2 meters per second squared times our 2 kilograms. So this would be a force of 4 newtons right there. Okay, so I guess what I'm saying is the answer is E, right? An acceleration graph will reflect a force of acceleration versus time graph will reflect force versus time graph, but they'll just be off by a value of whatever the mass is, right? So if this was 2 meters per second here and the mass was 2 kilograms, 2 meters per second squared here acceleration, and this is 2 kilograms, then this would translate to 4 newtons, because 2 times 2 is 4, right? So there you go. Well, now we're on Newton's third law of motion, and this is probably the weirdest one, right? Essentially it says this: if you push, forces are always equal and opposite. Okay, that's the very quick and awfully reduced way of talking about it, but force is always equal and opposite. So if you push on a wall, it pushes back on you in the opposite direction. Okay. But typically the weird part is the consequence of this, right? So if you imagine that you get into a tug-of-war match with an elephant, well, that elephant is going to just yank you off your feet and probably drag you really quickly towards it. Now, if I were, after the elephant did that, and I walked up and asked you, do you feel like the forces are equal and opposite? Of course you're not going to say that. You're going to think that's weird. Well, first of all, you'll be a little discombobulated that you just got yanked off your feet by an elephant, a cute, cute, sweet elephant. But really, while you were pulling on that rope against that elephant, and the rope was taut, not slack, you could say that the forces are equal and opposite. Your accelerations were not equal and opposite, but your force was equal and opposite, okay? But that's the thing. It's more, we struggle more with the consequence of this. It's actually easy to accept forces are equal and opposite, but then when you think about the consequence of that, well, why did I get yanked off my feet when the elephant didn't? Right? Well, essentially, the elephant has more mass than you, so it's not going to have much of an acceleration. But while you were pulling on each other, the force is equal and opposite, okay? But let's just go through the mechanics of this as far as teaching about force pairing. and then we'll talk about the consequences of it, okay? So you have to identify an action and a reaction force, okay? So if you have an object here, I'll draw a little block. Draw a little block here, okay? And you have a block here that is up against another block here. Actually, so you have two blocks that are up against each other, right? Well, this one block here, so this is block 1 and this is block 2, right? They're up against each other. So block 1 is going to feel block 2 leaning up against it. So just imagine that you're standing here and then your friend comes up and starts leaning upon you, right? Well, you are going to feel, block 1 is going to feel block 2 pushing it to the left, right? And so that's block 2 pushing on block 1 to the left. So I'm putting a negative there, right? Well, again, your friend, by the way, let's say might feel opposite. You were standing there, they walked up, and then you began leaning on them. Well, they would feel you pushing them to the right. And that's block 1 working on block 2, right? So this is what is called force pairing or action-reaction, right? If block 1 pushes on block 2, then block 2 is going to push on block 1 in the opposite direction, okay? And that this force right here of block 1 is only, this force right here only is existing because block 2 is working on it. And when that happens, two forces actually result when two objects are in contact with each other, or interacting with each other, I should say. And that, in this case, when block 1 is interacting with block 2, you create two forces that actually cancel each other out, right? The overall net force of this is going to be 0 because this force is equal to this force. It's just in the opposite directions. So they have the same magnitudes, just opposite directions, okay? And so that's kind of the case that we have right here. Block A is feeling a force on it from block B, and then block B is feeling a force on it due to block A. Okay, so this force pair is force of object 2 working on object 1, and this is object 1 working on object 2, right? So if I push on you, you push back on me in the opposite direction. Essentially, that's kind of the wording that goes on there, okay? And so it's always object A will work on exert a force on object B, and then the reaction pair will be object B will be working on object A, right? So the tire pushes on the road, and then the reaction force is the road pushes on the tire, right? Or a rocket pushes on the gas pushes on the rocket. Or a man pulls a spring, the spring will pull on the man. The earth pulls on a ball, the ball pulls on the earth, right? They're action-reaction pairs, right? And that last one is kind of a weird thing, right? If you have basically you have a weight, right? So you're standing here on the earth, right? Minding your own business, right? Well, that means the earth is going to give you a mass times gravity pointed down. Well, the reaction pair is this. You're going to be pulling the earth back up towards you an equal and opposite amount. Now, that doesn't mean that the earth is going to be falling upwards towards you at the same rate that you're falling down towards the earth. That's the acceleration thing. But what that means is forces are always equal and opposite. So your mass times gravity is equal to the Earth's mass times gravity upwards, right? The Earth is pulling your mass times acceleration of 9.8 meters per second squared down. Well, the reaction pair is going to be the Earth's mass being pulled up at 9.8 meters per second squared upwards, right? And that is true. That, I swear that is true, and it's the weirdest thing. The Earth is accelerating. When you jump off a diving board and you are falling down towards the earth, in a perspective, the earth is being pulled up towards you. Now, how much the earth actually does move is based on acceleration and its mass, right? Which is huge, so it's not going to have very much of an acceleration. But it will have an acceleration on it, according to Newton's third law. Okay? Well, that's kind of why we see tides right here, right? Because the action-reaction pair here is this. The water has inertia, right? So you have water on the side of the earth, and when the earth is being pulled towards the moon, well, it's kind of pushing that water this way. So the water here is being pulled towards the moon too, and then the earth itself is being pulled towards the moon as well. But this water over here wants to stay in place. So it actually is bulging out in the opposite direction, right? And since it's further away, it's not going to have much of an acceleration on it, right? So you get this weird tidal bulge, right? This side of the tidal bulge right here is actually because it is actually being accelerated here. But the other side of the water here is actually trying to stay in place, and the earth itself is being pulled to the right. So you get this weird tidal bulge that goes on. And it's a result of the action-reaction pair of the earth and the moon. The earth is pulling on the moon is pulling on the earth. So it's kind of cool, isn't it? Some astronomers might disagree a little bit with some of the words I said, okay? But that's a very reduced, very quick explanation for high and low tides, right? High tide over here, low tide here, right? If it's high tide here, the water here is going to not be too thick, so you can see that. And then you get high tide 12 hours later. So you get high tide twice a day and you get low tide twice a day. Okay? Well, let's try some stuff out. Let's try just seeing if you could identify action-reaction pairs. So a mosquito runs head-on into a truck. Poor little mosquito. It goes splat. What is true about the collision? Is it A, the mosquito exerts a force on the truck, then the truck exerts a force on the mosquito? B, the truck exerts more of a force on the mosquito than the mosquito exerts on the truck? Or C, the mosquito exerts the same force on the truck as the truck exerts on the mosquito? D, the truck exerts a force on the mosquito, but the mosquito does not exert a force on the truck? Or E, the mosquito exerts a force on the truck, but the truck does not exert a force on the mosquito? So A is mosquito exerts more of a force on the truck than the truck exerts on it. B is the truck exerts more of a force on it than the mosquito. C, they exert the same force. D, the truck exerts a force on the mosquito, but the mosquito does not exert a force on the truck. And E, the mosquito exerts a force, but the truck does not. So which do you choose? A, B, C, or D? Well, the answer is C, right? When the little mosquito, we'll draw a little fuzzy thing with little wings, is hitting the truck, so it's hitting the truck, okay? And I know this doesn't look like a real truck. Don't judge me about my horrible drawings. All right? This is a lot like this problem that we did over here, right? So at this moment that they're in contact with each other, the mosquito is being pushed, is feeling the truck on its right-hand side, pushing it to the left. So this is the force of the truck on the mosquito, which is to the left. And the truck is going to feel a force on it to the right, the same amount, and this is the force of the mosquito acting on the truck, and it's to the right. So they are equal and opposite, and that's the force pair. Let's try another one to see if you can identify force pairs. Okay? So bird flies. How does a bird fly? Well, it just flaps its wings, or does it push the air down so that the air pushes it upwards? Or does it just simply hover in midair? Or by inhaling or exhaling air? What do you think the answer to this is, right? Well, let's draw a little birdie. Little tail. He's got a little beak, a little body, and here you have his wings, or her wings rather. So basically what's happening is the wings are pushing down on the air. So just imagine a big poof of air, right? So the wings are pushing the wings are pushing down on the air. Let me remove that arrow, actually. So I'm going to imagine that there's just a big poofy air. So this is just air right here. So the air is going to feel a force pushing down on it. And this is the force of the bird on the air. And so that'll be downwards, right? But the air is then going to push straight back up in equal magnitude but opposite direction, and that's the force of the air acting on the bird. Okay? So that's the force pairing. So the answer to this is B. Okay? All right. Let's try another one. So you have, how does a rocket fly? How does a rocket take off? Right? So a rocket engine exerts a force of hot gases expelling out the back of the rocket. The upward motion of the rocket is caused by the hot gases rushing out the engine and then pushing against the ground and then pushing against the air or pushing back on the rocket engine. All right, so which one of these is true? Okay. So here is the rocket engine, right? So you've got gases being pushed down. So imagine a big poof of gases being pushed down, right? So this is the force of the gas of the rocket. Force of the rocket on the gases, and that's going to be down. And so these gases are going to be pushing on the rocket upward the same amount, and that's going to be force of the gases on the rocket. Okay, so that it doesn't need the ground to do that because rockets work in midair, and not only do they work in midair, but they also work in a vacuum too. So the answer is 3. A rocket flies by the gases inside it being pushed down, which then in turn push the rocket up. So compared to so if you have two gliders, you have one glider here, and I'm going to just draw an airplane here, and then you have another glider that has twice the mass, so it's twice as big of this other glider. So this is just one mass, and this is 2 mass, right? So you have a heavier glider and you have a light glider. In order for them both to maintain the same elevation, okay, compare the amount of downward force by the light glider to the heavy glider. What do you think? Who's going to have, or will they be the same? So a heavier glider will have to push air downward with a greater force, with the same force, or with a less force than the one mass object. What do you think? Well, equal and opposite forces again, right? So if this is a little bit of air right here, the air is going to get pushed down this amount by the mass object on the air, right? And that'll be downwards. And then that same force will be pushed upwards, and this is the force of the air on the mass object, upwards, right? Well, if you have a heavier object right here, it's going to need a lot more force down. It's going to need twice the amount of force down. So this is a 2-mass object. And so in order to maintain the same altitude, it's going to have to push down with twice the amount of force so that that air can push back up on the 2-mass object. Okay, so with a greater force. That's the answer. Spring scales. So one of the most reliable pieces of technology that we have for measuring force is a spring scale, right? And that's just a little spring. We know how much tension is in that spring, so how much of a force do you need to apply it, and we could actually create these things consistently such that they will consistently measure a same weight, a same force. Okay, so you have a spring scale right here, and it's held in place by a 5 Newton weight, and then you have another 5 Newton weight hung over this other side of this pulley system, right? So what is going to be the overall force working on this spring scale? And then what would the spring scale be reading? Okay, so this is a really good application of that Newton's third law. So what do you think is going to happen? So please read these choices and try answering the question. Well, if you think about it, you have this rope right here with a weight pulling down. So this weight is going to be pulling down 5 newtons. Okay, which is going to then pull this rope down 5 newtons, which means it's going to pull this rope to the right 5 newtons. Okay. Well, you have this other one that this is pulling 5 newtons down right here, which is then going to be pulling this rope down 5 newtons, which is then going to pull this part by 5 newtons. Okay? But this part of the spring scale is just attached to the entire scale. It doesn't have a spring attached to it. It's just, this force right here is essentially just holding it in place, while this other one will be pulling it to the left by 5 newtons. So we know the spring scale is only going to, so the spring scale should only read 5 newtons. This is just holding it in place, while this other one is just pulling it, right? So if you grabbed the left part of that spring scale and just pulled it to the left, well, this would just read 5 newtons, which is essentially what you're doing right here. But the overall tension on this object, okay, the net force on this entire object is going to be 5 newtons to the left plus 5 newtons to the right, which is going to be a total of total force is going to be negative 5 newtons plus 5 newtons, which is going to be 0, right? So the net force is going to be 0 on this, but the reading on the scale is going to be 5 newtons. So the overall scale has a net force on it of 0, but this part is just holding it in place as this spring is being pulled to the left, so that's going to read 5 newtons. So that's kind of an easy, kind of cool problem to try out. So there's a set of problems where you have to integrate the third law with the second law, and essentially, basically this. If we're going to be applying Newton's third law to show that forces are equal and opposite, so we're going to be doing tug-of-war problems, but we're going to be explaining the reason why people accelerate more when you're in a tug-of-war with an elephant, even though the forces are equal and opposite. Okay, so what this first part is saying is if you have a greater mass, you're going to have a smaller acceleration as long as the forces are equal. Here, you have a smaller mass, your mass goes down, your acceleration is going to go up, right? So we're going to be applying this to the Newton's third law, okay? So here we go. Salmon mass Sam and Sally have the same mass, but Sally is twice as strong as Sam. As each student pulls, they begin to reel each other in. Where will they meet? Will they meet in the center? Will they meet in the middle, in the center, which is option 3? Will Sam slide twice as far as Sally? Means option 1 is going to be over here. They'll meet somewhere over here. Or will Sally meet closer to Sam, which is option 2, is they're going to meet over here. So which one of these options do you think is going to happen? Will it be they meet in the middle, Sam meets closer to Sally over here, or Sally meets closer to Sam over here? What do you think? Try applying. So let's do this. So Sam is pulling on Sally, okay, and Sally is pulling back on Sam. So Sam feels a rope pulling him to the right, and this is the force of Sally on Sam. And then Sally is going to feel the same force, and we should put a positive there, to the left, and this is the force of Sam on Sally. Okay? Well, these two forces are equal, right? So this is the force of Sam on Sally, and this is the force of Sam on Sally, and this is the force of Sally on Sam. So this same force is equal and opposite. That's going to be equal to Sam's mass times Sam's acceleration, which is equal to Sally's mass times her acceleration, right? So if Sam's mass is equal to Sally's, that will be mass of Sally over the mass of Sam times Sally's acceleration. If those two things are the same, what this says is that Sam's acceleration should be equal to Sally's acceleration. Which means this: if their accelerations are equal, then their accelerations are equal. And as long as they both started from rest, they should meet right at number 3. So in these set of problems, what you're supposed to do is set the forces equal to each other. And then you evaluate one object's mass times acceleration, the other object's mass times acceleration. And then you solve for the acceleration. And so you could see that if one object has a higher mass than the other object, the accelerations may not be equal. Okay. Let's try another one. Sam and Sally have the same mass, but Sally decides to not pull the rope. She just ties it to herself and begins to reel. So where will they meet? Will they meet in the middle, which is option 3? Will Sam slide half the distance to Sally, which option 1 is right here? Or will Sally slide half the distance to Sam, which is option 2 here? So where will they meet if Sally now is choosing not to pull the rope? Before, just to remind you, she was twice as strong as Sam. That didn't matter. It was her mass that was important. Even though she's twice as strong as Sam, the forces are always equal and opposite. Well, now she's not pulling. She's got a rope tied to her. So what do you think? Please try it out. Well, essentially it's the same problem, right? So Sam is pulling on the rope, right? So Sam is going to feel Sally pulling him towards her, right? He's going to still feel Sally working on him. And she's going to definitely feel Sam pulling him towards her. right? So again, it's the same problem. You have the force of Sam on Sally is equal to the force of Sally on Sam in the opposite direction. This is the mass of Sam, the acceleration of Sam, and that's equal to the mass of Sally times the acceleration of Sally. And since their masses are the same, those two are going to drop out. So essentially Sam's acceleration again is going to be equal to Sally's acceleration, which is then going to be 3. They're going to be right in the middle. Let's do one last one. Sam is twice the mass of Sally. So this is me. This is me. So I've got a bit of a belly. Let me say that. I got a bit of a belly right here. And I'm now pulling on Sally, who is half my mass. So where will they meet? Will they meet in the middle? Will Sam slide twice as far as Sally, which is option 1? Or will option 2, will Sally slide twice as far as Sam? What do you think? Well, we're going to do the same approach that we have always done. Set the forces equal and opposite. So this is the force of, so when he's pulling the rope, he's going to feel Sally resisting him. So Sally's going to be working on Sam on this, and pulling him to the right. Well, Sally is going to feel Sam pulling her towards the left. Okay? And Sam has twice the mass of Sally. So forces are equal and opposite. But Sam is twice the mass, and this is the Sam's acceleration of Sally, right? And Sally has just one mass. So this is the acceleration of Sally, right? Well, those masses are going to drop out, and you're going to divide both sides by 2. So what is this saying? I divide both sides by 2. The acceleration of Sally divided by 2 is equal to Sam. So what is this saying? Well, this is saying that Sam's acceleration is going to be half that of Sally's. And that Sally is going to have a much longer acceleration. Sally's acceleration is going to be twice as Sam's. So Sally's acceleration is twice Sam's. So she's going to have a much higher acceleration than Sam because she's lighter, which means they should meet here at 2, right there. So when you get in a tug-of-war, this is you in tug-of-war with an elephant who's really heavy. It's not that the elephant is strong, it's because the elephant is heavier than you, right? You're going to accelerate more. So Sam is going to have a lower acceleration, which means he's going to actually move less than Sally. And Sally's going to have twice the acceleration, so she's going to move twice the distance that Sam is, right? So for every step he takes to the right, she's going to take 2 steps to the left. So they're going to meet closer to Sam than Sally. All right. Well, I hope you liked this overview of Newton's 3 laws. We're going to now move on in the next unit about how to create force diagrams. So rather than doing total force diagrams of action-reaction pairs, we'll just concentrate on one object and do a force diagram, or free body diagram, they're also called, on one object. All right? Bye!